Welcome. Today we're diving deep into the design behind the leading video conferencing platform. Let's explore how to build your own Zoom-style system.
Imagine a critical all-hands meeting. Suddenly, latency spikes to 10 seconds, and 60% of participants experience frozen video. The core video service collapses under the strain of 10,000 concurrent streams. A naive solution involves a mesh network, where each participant sends video directly to every other participant. This works well for 3 people, but melts your CPU for 100. Each client needs to encode and decode N1 streams, quickly overwhelming resources and causing the dreaded video freeze. Why does the mesh network fail at scale? Because each client is doing too much work. Encoding and decoding video is CPU intensive. With 100 participants, each client needs to handle 99 streams. This leads to quadratic complexity, n squared. Enter the Selective Forwarding Unit, SFU. Instead of each client sending video to everyone, they send it only to the SFU. The SFU then forwards the video streams to the appropriate participants. This reduces the client's workload to a single encode, dramatically improving scalability. Now that we've established the SFU architecture, let's enhance our system's ability to handle varying network conditions. To achieve this, we'll implement simulcasting. Simulcasting allows the SFU to adapt to each participant's bandwidth. With simulcasting, each client receives a video stream optimized for their specific network. A 4K monitor gets a high-definition stream, while a 3G phone gets a standard-definition stream. This adaptive approach ensures a smooth viewing experience for all participants. Let's discuss network resilience. It's crucial to differentiate between signaling and media transmission. Signaling uses WebSockets or HTTP for call setup. Media, on the other hand, utilizes UDP or RTP for transmitting video packets. Separating these is key for managing disruptions. To prevent choppy audio, we introduce a jitter buffer. A jitter buffer adds a small delay, typically 20 to 50 milliseconds, to smooth out variations in packet arrival times. This 20 to 50 milliseconds trade-off drastically improves audio quality. Now that we've covered the importance of separating signaling and media, along with the role of the jitter buffer, let's delve into how we can ensure smooth video delivery across various network conditions. To further optimize video quality, we employ Scalable Video Coding, SVC. SVC lets the server send multiple layers of video quality to the client. These streams are optimized for diverse network conditions. A 4K monitor gets HD, while a 3G phone gets SD simultaneously. This maximizes the experience for each user, optimizing client CPU versus. SFU architecture balances client CPU and server bandwidth. However, what happens when the SFU server itself becomes overloaded? Building on the SFU architecture, we need to consider network resilience. Signaling, which handles call setup via WebSockets, is separate from media, which transmits video packets via UDP. A lost signaling connection means call termination. To combat choppy video from dropped packets, we use a jitter buffer. This buffer introduces a 20 to 50 milliseconds delay, smoothing out variations in packet arrival times. The trade-off is increased latency versus a more stable video stream. To manage this complexity, we use Envoy Proxy, which we configured earlier, to route media streams based on network conditions and client capabilities. Envoy dynamically adjusts stream selection, optimizing for bandwidth and minimizing latency. To monitor the performance of our video conferencing system, we use Prometheus to track key metrics like stream latency, packet loss, and jitter buffer utilization. Now that we've covered jitter buffers and packet loss mitigation, let's examine scaling strategies to support a large number of concurrent users. The key is understanding the trade-offs between client-side CPU usage and server-side bandwidth consumption. We can use different SFU topologies to balance these factors. In a hierarchical SFU, edge SFUs handle direct connections with clients, reducing bandwidth load on central SFUs. Central SFUs aggregate streams from multiple edge SFUs for large conferences. This approach allows the system to scale horizontally by adding more edge SFUs as needed. Finally, let's address monitoring and observability. Building on the Prometheus setup we previously configured, we need to track key metrics such as SFU load, stream quality, and user experience. Grafana dashboards provide real-time visibility into the system's performance, allowing us to identify and address bottlenecks proactively. In conclusion, designing a scalable video conferencing system requires careful consideration of architecture choices, media strategies, and network resilience. By leveraging SFUs, simulcast, jitter buffers, and robust monitoring, we can deliver a high-quality user experience even at scale.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.